In this module, we'll work with verifying identities. The purpose of working with identities is that sometimes we run into trig equations that are rather complicated on one side of the expression. And if we can go through and simplify that side, make it a little bit easier to work with, that can make solving equations a lot more manageable, a lot more reasonable. There's a couple of very common identities. One of them is probably the most basic one, called the Pythagorean identity, and you'll see why here in just a little bit. Sine squared of x plus cosine squared of x is equal to 1. So no matter what value I substitute in for x, no matter what angle measure I choose to use there, if I take the sine squared of that angle plus the cosine squared of that angle, I'm always going to get 1 for an answer. Okay, now why does this work in this fashion? Well, let's look at it from a geometric viewpoint. If we think back to our unit circle and just pick a random point on our unit circle, the coordinate for that point is cosine of x, sine of x. And don't forget the hypotenuse on a unit circle, or the radius on a unit circle, is equal to 1. Now, if I was to drop a right angle from that point and take that triangle and make it a little bit bigger so we can work with it, we would recognize that the hypotenuse of that right triangle is 1. The x-coordinate is described by the cosine of x, and the y-coordinate is described by the sine of x. Now just use Pythagorean's theorem, and you quickly see that cosine squared plus sine squared is equal to 1 squared, or 1. Most of the time we don't use a geometric viewpoint to try to prove identities, but for this one, as it is so basic and it has such a nice geometric proof, this seemed to work out well for this example. Other types of examples we might work with more of an algebraic approach to them. For example, what if I'm working through an equation and on the left side of my equation I have a 1 plus cotangent squared. Now what I'm curious to see, does this simplify to something that's a little bit easier to work with? The algebra viewpoint on this is, first of all, try to take any co-functions like a cotangent and rewrite them back in terms of either sines or cosines. By definition, cotangent is cosine divided by sine, so cotangent squared would then be cosine squared over sine squared. Now, the algebra trick that I can use at this point is to rewrite 1 as sine squared divided by sine squared. My purpose in doing this is so that I have a common denominator on both my terms on the left side. Once I have a common denominator, I can simplify the left side as 1 fraction instead of 2. And if I look up in the numerators, when I join these together, I have sine squared plus cosine squared. We just decided on the previous slide that this is equal to 1. So now I've simplified the left side to 1 fraction. It's 1 over sine squared, and by definition 1 over sine is equal to cosecant, so 1 over sine squared should be cosecant squared. So if I'm ever working with an equation and I see a 1 plus cotangent squared, I could rewrite it as cosecant squared. Might make the problem a little bit easier to work with. At this time, you should try to do something similar for the following. Tangent squared plus 1 equals what? This is another very common identity that we replace tangent squared plus 1 with something a little bit easier. You should pause the video at this time, try to find out what that other side of the equation is, and then restart the video to see if you're correct. Alright, for this example, we can use a similar approach as what I have on the left-hand side of the slide. I can take and rewrite this tangent squared as sine squared over cosine squared. I can rewrite the 1 as cosine squared over cosine squared. And then by joining these together, with my common denominator of cosine squared, I see that the numerator again simplifies to a 1, and then by definition 1 over cosine squared is secant squared. So again, a very common one is that secant squared is equal to the tangent squared plus 1. Another approach that is sometimes used in proving identities, although this is a little bit harder to see, it's a little bit more advanced of a technique, is if you start with a known identity. Start with something that is true. Sine squared plus cosine squared is 1. And then start working off of it. Do things to this equation and come up with new identities. For example, one of the things that sometimes is done is let's come in and just divide all of our terms by cosine squared of x. And see what comes out of it. Well, sine squared over cosine squared, that's just tangent squared of x. Cosine squared over cosine squared is 1, and 1 over cosine squared, there's secant squared. And this is the identity we just proved on the previous slide. So this is another way that different identities are developed, is to once you have a few identities at your disposal, start doing things to those, manipulate them a little bit, and you can come up with new identities. Now, not all the identities are going to work quite as easily as the ones that we've run into so far. They can get to be very, very difficult, very complicated. But let's look at another example here, just see if we can find some algebra tricks to work our way through an example like this one. The claim is that the left side of this equation is equal to the right side of this equation. And it's our job to use some kind of algebra to verify that, yeah, this really is a true relationship. Okay? In terms of an equation, most people would probably rather work with the right side than the left side because nothing is squared on the right side. It's a little bit easier to work with things that are not squared. The approach on these type of problems usually is to start with the more difficult side and work your way back, trying to simplify to get to the simpler side. So let's look at this as a possibility here. Now, on the left-hand side, I have a 1 minus cosine of x quantity squared. So what I'm going to choose to do is write that 1 minus cosine of x squared as 1 minus cosine of x times another 1 minus cosine of x. Now, as I look at this, I see that, oh, this denominator is very close to the denominator on the right-hand side. So at the same time, I'm also going to do a little bit of work on the right side of the equation and see that, okay, if I multiply by another 1 minus cosine of x on the right side, my denominators will match up. And this is supposed to be a cosine of x in here. So as soon as I get my eraser, I'll clear that out and rewrite it. Now, at this point, I'm trying to make the numerators match up because the denominators are already equivalent to each other. At this point, I'll go ahead and do a little bit of distributive property, FOIL, on the right-hand side and see what I come up with. So 1 times 1 is 1. The outside's 1 times negative cosine of x. The inside is a positive cosine of x. And the last times the last is a minus cosine squared of x. And in the denominator, I'm going to write this as 1 minus cosine of x squared. Now, the cosine and the negative cosine cancel each other out, and if I look in the numerator, 1 minus cosine squared is equal to the sine squared of x, and that is exactly the part that we were trying to get to match up. So what you may also do on some of these is you may end up multiplying by 1 in a nice disguised form, 1 minus cosine of x over 1 minus cosine of x, in order to get your identity to come out. Okay, to conclude this module, I'm going to write one more identity on the screen here. 1 over 1 plus cosine of t plus 1 over 1 minus cosine of t equals 2 times the cosecant squared of t. I'd like for you to take a couple of minutes, try to prove that the left side of this identity is equivalent to the right side of this identity. Go ahead and pause your video at this time. Alright, the left side is definitely more complicated than the right side, so we would definitely like to see the right side come out as a true expression. In this case, I want to get a common denominator, and it looks like my common denominator needs to be 1 minus cosine of t times 1 plus cosine of t. In order to get this to work, I need to multiply this first equation by 1 minus the cosine of t over 1 minus the cosine of t, and I need to multiply the second term by 1 plus the cosine of t over 1 plus the cosine of t. Then I'll start putting these together. Now, the other thing I can look at here is start distributing through in the denominator. So 1 times 1 is 1. The outside gives me a negative cosine of t, and the inside gives me a positive cosine of t. So those will cancel. And then last times last is negative cosine squared of t. Up in the numerator, I have the common denominator already, so I'm just joining all of these terms together. Looks like the cosine of t and the negative cosine of t cancel off, and so I just have 1 plus 1, or 2. The denominator is 1 minus the cosine squared, but if we think back to that, sine squared plus cosine squared equals 1, so it looks like this should just simplify to sine squared of t. Because if I take the hypotenuse squared minus one of the legs squared, I should get the other leg squared. And then we see 2 over sine squared is equal to 2 times cosecant squared. And so this is our final result. Like I said, the big thing, usually you will not know where you're going with these. So you wouldn't be given the right side. You're just going to start playing around with the left side, simplifying it, hoping that it runs into something that's a little bit more manageable to work with. Okay, but if you can have basic identities like sine squared plus cosine squared equals 1, or tangent squared plus 1 equals secant squared in your mind, that can help simplifying these identities or these difficult trig expressions can make it a lot easier to work with.